So welcome to the lecture on process switching. So we will see how the context switch process exactly works. So it is a far more complex mechanism than what we have thought of. So let's look at some of the general principles. So every process, as we will see, has a hardware context and has a software context. So the hardware context is something that you need to store and restore. But the software context, such as the open files, network connections, even the memory contents, they are not something that you have to store and restore. So the hardware context, which is of great importance, comprises all the general purpose registers. The program counter is referred to as the instruction pointer in x86. All the segment registers. So segment registers FS and GS are primarily used in x86-64, whereas earlier versions of x86 tended to use more segment registers. Then privileged registers. So privileged registers, a user mode program doesn't use a lot, but one of the interesting ones that it uses is actually CR3, which stores the base address of the page table. So it is true that this is a part of the context, but we will try to ensure that this base address is not updated very frequently, because updating the page table, so the moment that you change this, the page table will get updated and automatically the TLB will also get flushed. And these are very expensive operations, extremely expensive. So we want to update the CR3 register as infrequently as possible. This is our explicit aim. Along with that, we'll have ALU and floating point flags, which basically store the status of instructions that have executed in the past, but have a bearing on the present and the future. Namely, if a comparison was done in the past, it sets some flags. And these flags are used to decide the direction of conditional branches in the future. Hence, there is a need to actually store this as a part of the hardware context and restore it as well. The page table and the TLB, these are important things which will sort of be the mainstay of our discussion in this section. We have not talked a lot about this in the past, but we will see that changing the page table and the TLB is strictly discouraged. It's a bad idea. The reason is that the performance penalty of actually moving to a new page table, which also implies that you're moving to a new TLB contents, new set of TLB contents. This makes the system very, very slow, right? So it will increase the number of TLB misses manifold, which is not a good idea. So we will keep on discussing this, but kindly remember that we have put a question mark here, which means that we'll keep on revisiting this issue several times in this class. The software context, namely the open files and network connections, is way easier to manage, along with the time that a process is executed, all other metadata information. The main reason being that these are not part of, these are not ephemeral, so they don't go away. They are part of the task struct and they will remain where they are. They will safely remain where they are. There is nothing that needs to be done about them. So coming back to what we have identified as the main problem, which is the TLB and page table, and the fact that we don't want to change their contents on every switch. We want to do something and optimize. So what are the kind of switches that are possible? So if you are a user process, let's say, you can go to the kernel. If you are in the kernel, let's say you can switch from one thread to another thread. So you can have a kernel to kernel. And then when you go back to a user process, then you can do K to U. User to user is not possible, mainly because you'll have to go via the kernel, which is captured in these cases, the three cases above. Also, when you're going back from the kernel to the user, there are actually two sub-cases, and the sub-cases are reasonably important. The first sub-case is, it is the same user process that got interrupted and the kernel came. You're kind of going back to it. So let us call this the same case. The other cases, you are loading a different user process, so it's same and diff. So basically, these are the 4 situations that you are looking at, where we can look at, where we can call this 1, 2, 3A and 3B. So these are the 4 cases which I am numbering 1, 2, 3A and 3B. And the idea here is to propose some optimizations given that these are our 4 sub cases. So let us look at some facts that we have also mentioned in the past, but those facts become very important inputs for the current discussion. The first is that all kernel threads share their virtual address space. All right. So all kernel threads will share the virtual address space, which basically means that the kernel virtual address, regardless of the kernel thread, resolves to the same physical address. This is fact number 1. Second is that the virtual address space, be it any kind of thread or process, is split between the user part, which lies at the bottom, and the kernel part, which lies at the top. So the split can be, different for different architectures, but this is kind of something that holds universally. Quintessential example in this case is 32-bit x86, where you have 32 bits, so the total size is 4 GB. The bottom 3 GB is for user, 1 GB is for kernel. And Windows is slightly less charitable towards the user, so it's 2 and 2. But again, as I said, in 64 bits, you have a lot of space. Here also, there is a similar kind of split. Now, what happens is that the kernel part of the mapping, this part is identical or constant across all processes. So for all processes, the upper part of the address space, which is also captured in the page table, is constant. And the process clearly cannot access these addresses because they are in the kernel zone. The TLB will figure out that they are in the kernel zone, so it will not even give it a valid mapping and it will raise a fault. So the user process, for the user process, this is a no-go zone. But what happens is that if you change the user process, for example, I was executing, let's say, Notepad, and then I do a context switch, which means I go to the kernel and so on. But after Notepad, let's say Internet Explorer is executed. What will change is basically the user portion. The kernel portion will remain the same. Right? So this is something that we have discussed up till now. And this discussion becomes more so, even more relevant in our current discussion, because we will use it to actually optimize our design, and this we have not done in the past. So there are 2 options that we can do. The first is, so if I consider the user-to-user case, this is option 1, option 2, that I append the PID with every TLB entry. So with every TLB entry, I say this belongs to this process ID. This is problematic in many ways, even though this solution is actually used on x86 machines, because the PID is a software OS concept. The TLB is a hardware concept. Now the question is that within a TLB entry, you keep some space and then you put the PID here. You have to look at a bunch of corner cases. What if this is, let's say, how many bits will you put here? 10 bits? 10 bits is a maximum of 1024 processes. What if I have 1025? So this does create a little bit of a problem, but Intel processors still have this, and this is very effective. The other is that if the PID is not there in a TLB entry, then if I'm doing a user-to-user switch, the TLB has to be flushed, or at least all the user level mappings have to be flushed, and the page table has to be changed. So typically TLB flushing and changing the page table happen together. So this has to be done if I'm moving from one user process to another, if these PIDs are not supported. And as I have said, supporting this is breaking a few abstractions. In the sense, you are making hardware be aware of a software level concept, right? Which is problematic. Ideally, software should be aware of hardware, but not the other way around. So this is, in a sense, breaking that classical separation that exists. But as you can see, there is a performance gain here. But if we ignore that, then we will have to flush the TLB and reload a different page table if PIDs are not supported. So what happens is that let us now use the insights that were shown here. So if there is a user to kernel transition, if you actually think about it, there is no need to flush the TLB and there is no need to actually reload the page table. If you are not convinced with me, kindly memorize this and wait till the next slide. My claim is that if you are moving from kernel to kernel, like you are running one kernel thread, now you are running another kernel thread, there is no need to flush the TLB and there is no need to reload the page table. That is my claim. You need not believe me, but if you are not believing me, wait for one slide. Otherwise, if we are ultimately loading a different user process, that is an expensive event. That is where flushing and reloading are required. So as I said, some amount of skepticism is healthy. So let us look at this scenario over here that you are seeing on the diagram. So what you are seeing is that you are seeing the virtual address space of a process. So of course, you have a user space, you have a kernel space. The entire memory map of the user process fits within the user space. All right. So in the memory map, we know what all is there. We have the stack here, you have the heap here, which grows up. You have the text section, data section, and so on. So we know how the user memory map is organized. And the entire user space virtual memory is stores the memory map, right? So that is how the apportioning happens. On top of the user space, you have the kernel space. Kernel space means what? It's a range of virtual addresses and they are mapped to actual frames in memory. The same is the case for another user space, where this user space and this user space are actually different. In the sense that the same virtual address across these two user spaces will actually map to different physical addresses. But the kernel space on top, that is the same. Same means what? The mappings are identical, which basically means that the same kernel virtual address will map to exactly the same physical address. So the mappings are identical. Now you consider a pure kernel thread, which is not a user space thread. It was born in the kernel and lives its entire life in the kernel. This pure kernel thread will not have any user space component. It will still start from here. And it will again have identical mapping, same mappings. So the advantage of this is very obvious, that let us say I'm running a user mod program. And then the program does a system call. So as we have discussed earlier, there is no reason to start a new kernel thread to take care of the system call. Temporarily promote the user thread to kernel. So you set a bit and temporarily promote the user thread to be a kernel thread, change its stack to some other stack, and set the CPU to the kernel mode, ring 0. Now the promoted user thread can happily operate in kernel space, which is this space. Correct? There is no need to change any mapping. It can continue to use its TLB mappings and the page table mappings for this part, right? The page table mappings for this part. And this time there will be no error, right? Why will there be no error? Because as a user thread, if I'm trying to access kernel space in user mode, it can easily be detected that, look, your privilege level is much lower than what is required. But when I have been temporarily promoted to kernel mode, then I can happily access kernel space, right? Those access and protection restrictions do not hold for me. Correct? So far, so good. So that is why I actually can easily operate in kernel space. And then again, when I come back, I start operating in this space. Similarly, if I consider another user thread, then there also there is no need to flush anything or reload anything if I go from user to kernel. Now let's say that this promoted kernel thread gets swapped out. Another pure kernel thread starts running, and this is not promoted. It started its life in the kernel, lived its life in the kernel. There is no reason to change any TLB or page table because that will also be mapping exactly the same virtual address space with the same mappings, right? With exactly the same mappings, it will have them. So no TLB is flushed, no page table is reloaded. Pure kernel threads can keep working. There is no problem at all. The problem will arise when from here I am trying to transition to a user thread, right, which is different. If it is same, which means that let's say if this thread is restarting over here, then there is no problem. Because in any case, I'm using the page table of this thread, right? So there is no problem at all. So I can just go back and the same old page table will be used. There is no problem at all. Correct. So I didn't change my page table up till now. I went from user to kernel, kernel to kernel. Same, this page table is continuing. The problem will begin if, let's say, when I want to run a user process, it is something which is different from what was previously running, which means it is this case, the diff case. Correct? In this diff case, the user space part, which is this part, has to be changed, which means that for this part, I will have to flush the TLB. I'll have to reload a new page table, which corresponds to the page table of the new process. That is the only expensive case. That is why my scheduler should ideally always try to continue the process that was executing, try to resume that, as opposed to starting a brand new process, because that has this overhead. So the key point here is that there is a need to perform an expensive operation, namely flush the TLB and also clean up CR3 and load a new page table, only when some kernel thread transitions to a user level process which is different, which is basically at case 3b, which is not the same as the original user process that was interrupted. That is only when we'll change the page table. Otherwise, there is no need. The same user processes page table can be used for doing all kernel work and even switching between kernel threads, because the kernel part of the mapping is the same. So once we have understood this, and this is a very crucial piece of knowledge for us, let us look at the three individual types of context switches. So as I said, we can have a full process context switch, where the process is kind of a single threaded process, so it's not a part of a thread group. Then we can have a thread context switch and an interrupt context switch. So let us see what these things are, and then we will see. So consider a regular process that is entering the kernel after a system call. So we have already argued that there is no need to create a separate kernel thread. The same thread can continue. The same thread can simply become a kernel thread and continue. It is just that whenever there is a system call, the CPU mode or the CPU ring level transitions from user to kernel. So it becomes ring level 0, and then you let the same process continue. In the continued mode, it becomes a promoted kernel process, so it can access all kernel pages. So the first thing is that if you need to save after a system call, the hardware context needs to be saved. In the hardware context, there are certain very important parts like VIP members of the hardware context. So clearly the most important is the program counter. That is because if we execute anything else, the program counter will change. So the original program counter will be lost. That is why we need to store it. And once the context is stored, the thread can continue to execute in kernel mode. So this is not a full switch, but rather it is a soft switch where there is a context saving and the mode of the process is changing. So this is of course less complicated than a full-scale process switch. And as we will see, the virtual address spaces will remain the same. So it's not can, but will remain the same. It is just that we'll change the stack. So we will not use the user mode stack and we will use the kernel mode stack, right? So that is the major difference. Also, one more thing, in case you have not appreciated, is that let us say that some kernel thread or maybe the same user process which has been promoted to be a kernel thread wants to access some data in the user space. And it's very common to want to access such data, for example, because if I want to send, let's say, something over the network, then a buffer in my space, a pointer to a buffer in my space has to be sent to the kernel. Then the kernel will have to read data from the user space of a process. How will the kernel do that? In this case, the kernel can do it very easily because it is actually using the page table of the user process that was interrupted. The same page table is being used, right? So instead of using kernel addresses, nobody is stopping it from using user addresses. So if some array is stored here, the entire array can lock, stock and barrel be copied to a kernel buffer. All right. And given that the same page table is being used, there is no problem. Otherwise, there would have been a problem, but in this case, there is no problem. So this is how we run a process in kernel mode. And it is important to use a kernel specific stack because a lot of information, including the context, etc., has to be stored somewhere. And the best place for storing a lot of that information is on the kernel stack itself. It's also the work area for the kernel thread. And this cannot be the user mode stack, mainly for security reasons, because whatever you write in kernel mode should not be accessible to you when you go back to user mode. That's a crucial security thing, which is why a separate kernel stack is required. And in fact, we will see even when we process interrupts, a separate interrupt stack is given, but the same thread continues. That is the crucial efficiency optimizing step here. So let us now look at the most important question, which is how to flush the TLB and update the CR3 register. Updating the CR3 is tantamount to changing the page table, and these two actions happen together. In the sense, whenever you change the page table, the TLB also gets automatically flushed. So we will look at both of these actions in unison, and we will look at 4 specific transitions and understand, is there a need to do both of these? Because as we have argued, these are very expensive operations. So you do not want to change the contents of the TLB because this will lead to TLB misses, and a TLB miss is expensive. So consider a user to kernel transition, which happens if you have a system call or an interrupt. If that happens, then thankfully there is no need to do anything. Nothing at all has to be done. Kindly go back to this diagram. The kernel threads will use this space, and this space is already there. Every user process, this space is identical. Given that it is identical, absolutely nothing has to be done. If you are moving from kernel to kernel, again the top space is identical, nothing has to be done. The moment you are switching back from the kernel mode to the user mode, there are 2 subcases. The first subcase is when you have the same user process that was executing, the same one is going to come back. Then what you do is that you don't do anything because the same mappings are there, so you don't do anything at all. The only time in which you do something is when a different user process is coming. That is when there is a need to do a TLB flush as well as change the CR3 register, the page table. User to user is not a direct transition. You'll never transition from one user process to the other. It will always go via the kernel. Hence, this will not happen. This is kind of subsumed in the 3 earlier cases. So hopefully this explains to us how and why there is, the Linux virtual memory architecture has been created to minimize the number of TLB and page table switches. That has been our explicit aim. So now let us look at a thread context switch and understand some of the nuances Because as we can see, something may sound very good conceptually, but when you try to implement it, there are unique implementational challenges. So as we have discussed, a thread is an atomic unit of scheduling in the OS, and every thread is, so basically everything is a task. It has a task struct. The reason that we use the term thread is because of the virtual address space sharing with other threads in the thread group. So switching threads in the thread group should technically be easier than a full process context switch, right? It should be easy. That's what we think it should be. But how is it easy? That requires some further explanation. So assume you are switching from thread 1 to thread 2. Both are in the same thread group. Then first you have to do the obvious set of actions, which is store the context of the previous thread of T1, namely the registers, flags, PC, etc. Here is what we want to do. The reason I've put a question mark is because this is what we want to do conceptually. We have to find a good practical way of doing it, but this is what our desire is. So our desire is to replace only those parts of the virtual to physical mapping that are private to the thread, that are thread specific, namely the stack and the TLS region, where TLS stands for thread local storage. So this is what a thread exclusively owns. It owns its own stack, and it owns a small storage region which is local or private to a thread. That is what it owns. So you may want to argue that, look, you take the memory map as it stands, or the virtual address space as it stands. A large part of it is shared, nothing needs to be done. The part of it which is not shared, essentially the mappings for these should change. That's basically what we are saying, that the stack and the thread local storage region, those mappings have to change because the thread is changing, but the rest remains the same. Fair enough, but this doesn't sound very efficient, so we will revisit this topic in the subsequent slides. So let's anyways look at the next two steps. The next step is that we change the current pointer. We always do when you're moving to a new task. So we say that, instead of T1, T2 is the current task, and we restore the context of the current thread. All right. So these are the traditional boilerplate actions that we do. The only question that is there in front of us is, how do you replace parts of the virtual address space, right? So in a certain sense, you can think of it like a large painting, but there is a part of it that you don't like. So you want to cut out that part and put in another part, right? This is tough. It is cumbersome. We don't seem to like it, right? So what you can do is that let us start with a bold idea, and then we will figure out that it's not that bold after all. Why not adopt the same solution as kernel threads and say that all the threads share the same virtual address space in a thread group, right? It's in a thread group. Let's assume all of them share the same virtual address space. Fair enough, then there is no problem. But the problem is, what do you do about the stack, right? What do you do about the thread local storage? But let's consider the stack first. We'll look at TLS later. What do you do about the thread specific stack? Here is what you do. Kindly look at the common virtual address space. Don't worry about the stack for the time being. So you have the text section. This part is shared. No issues across all the threads. You have the data and BSS section. This part is shared. Again, no issues. You have the heap that is shared. Again, no issues. Now what you do is the same thing that you did with kernel stacks. You say that this is the stack of user thread 1, this is the stack of user thread 2, stack of user thread 3, so on and so forth. Then what will happen is that every thread will still have its private stack. All right. And you need to understand that the way that we address the stack is as an offset from the stack pointer. So every thread will still have its private stack. It is just that now all those private stacks will actually be in the same virtual address space. And when you start a thread, you basically say your thread number 3, all right, so this is your stack. Your thread number 2, no problem, this is where you are. So when you change a context, you don't have to do anything about the stack pointer, because it will go back to whatever was its previous stack pointer. So let's say you are going from T1 to T2. So T2, if his previous stack pointer was over here, that's where you're going to start. So the greatness of this idea, and the same thing can be done for the thread local storage as well, is that you can have exactly the same virtual address space for all the threads and still provide a different stack and a different private area to every thread. In the sense, you can still maintain the abstraction that they have separate stacks. Correct? And because you have the same virtual address space, whenever you switch between two threads of the same thread group, no page table or TLB update is necessary, which will save us a lot of performance. So let us explain this in another way. So assume that both of us are talking in English. So we will use an English dictionary. In case I say something and you don't know what it means, so you can refer to an English dictionary. Now let us say that in my place another teacher comes and he also starts speaking in English. There is no need to change the dictionary. The same English dictionary is useful. So, and the dictionary can be kept here. So I can have a small dictionary over here because there is not much space on my desk. That is like the TLB. And there can be a big fat dictionary there, right? And that is like the page table. The issue will arise when, let's say, another teacher comes who is not from my group. Let's say I am from the English speaking group. The other teacher will speak in Hindi. In that case, the dictionaries have to be replaced. The dictionaries are not smart enough to replace themselves. Whoever is switching me, like I am going out, so whoever decides that I need to go out and the new teacher needs to come in who will teach in Hindi, so that person is the operating system. That person's job, in this case it would be, let's say, the classroom in charge, will have to remove these English dictionaries, bring in Hindi dictionaries, place a small one on my table and a big one right there, and then the Hindi class can resume. So the same way, because all threads in a thread group use the same virtual address space, they can use the same page table. The problem arises when you go to a different process. That will require a different page table and consequently different TLB entries as well, which necessitates the need for a flush and for a switch in the page table. So now that we have discussed the thread context switch, which turned out to be much more complex than what we had originally assumed, let us look at an interrupt context switch, which happens when an interrupt arrives. So whenever a hardware interrupt arrives, often there is a need to service it quickly, and that too very quickly. So here also, instead of starting a new thread, we promote the existing user thread and we make it a kernel thread. And that goes and services the interrupt. And as we have seen, that it does not use its own user mode stack. It uses a separate interrupt stack, and every CPU has 7 interrupt stacks. So one of those stacks, the free one, it takes, it uses. So the interrupt code, which is known as the top half, that has a lot of restrictions. So the restrictions are like this, that, let's say, for example, consider that a class is going on, and then my department calls me for some small emergency. What I will tell them is that, look, I can't do a lot. You have interrupted me from a running class. Maybe I will do 15 seconds of work or 20 seconds of work and I need to go back. So this is a top half, and I'll say whatever is left, I'll do it tomorrow. So that deferred work is the bottom half. So the OS works in exactly the same manner. The top half is a very, very short piece of code subject to a lot of restrictions, namely that you can't, so the code size is typically limited or the stack size is limited. In theory, it can be very long, but this is more of a convention that you don't want to do a lot of computation here. You cannot acquire locks because, you never know when the lock will be released. Also, interrupt threads are a very high priority. So the other thread that is supposed to run to release the lock may actually never run. So that is why whatever work you want to do, which is of a more, You need more features like locks and so on. So you create a full-fledged kernel task that executes later. After the basic interrupt processing is done by the top half, you schedule some work for the future. That work is done by the bottom half thread that does the bulk of the interrupt processing, and that does not have restrictions with regards to what kind of code it can use. So it can use locks, it can use all kinds of blocking and non-blocking synchronization, which an interrupt thread cannot. The top half cannot. The top half obviously operates in a kernel virtual address space. And here also changing the TLB and page table is not required for the same reason. This is a kernel thread, so what's the need? And it uses its own stack. So as we can see, efficient virtual memory management and splitting. So what were the big broad ideas? The big broad idea was that we split the virtual address space between the kernel and the user, and the kernel part was kept the same, identical, across all page tables, including the page tables of kernel threads. That minimized the context switching overhead. The second big idea was that for different threads in a thread group, we do not replace the mappings for their stack and TLS sections. Instead, we actually place them in different parts of a common virtual memory, which is shared across all the threads in the thread group. That also minimizes the context switching overhead insofar as your TLB flush is concerned and page table switching is concerned.
So we are now done with providing a broad overview of the overall context switch process. So we have discussed the high-level steps and when there is a need for flushing the TLB and replacing the page table. So we will now look at the more low-level steps that are involved in the context switch process. This we will do in the next lecture.